All right, I'm gonna give you guys some time to work through these, and then we will get to them together. All right, so this first one here, we have this quaternary amine, which is from group 6, which makes it a meta director. So we'll either add these two symmetrical meta positions here. We have nitric acid and H2SO4, which means we're adding a nitro group. So our final product should be this here. Toluene is a group 3. Which means it's an orthopara director. So there should most likely be two different products in this reaction. One where we add this BR to the ortho position. And another one where we add a para. All right, our next one, we have two different groups on it. We have a group 1, which is this tertiary amine, still has its lone pair, unlike this quaternary one up here. We also have a toluene, or this methyl group here, which is a group 3. So we're going to favor the group 1. It's an ortho para director. It would add to this ortho. This ortho is blocked, or this para position. So we should get two different products. Looking at these two products, most likely this would end up being the major product. This is such a large group here that adding next to this amine would probably be very difficult. So the para one is probably going to end up being favored for these. Unlike this one up here, the bromine and the methyl are both pretty small. So we're going to get some sort of a mixture, and it's going to be hard to tell which one is actually your favorite product. And for the most part, you wouldn't need to indicate which one's major unless it's something extremely large. Okay, so steaming H2SO4, we're going to add a sulfonyl group. This is a group 4, which is still ortho para directing. So adding to one of these three positions, we're going to end up with two different products. Which would be these two here. Our next one, our chlorination, is going to be, this is a meta director, this is group 5. So we should add our Cl to one of those two positions. They are symmetrical. And we can get this product. Our next one, we have methyls, which are group 3. This amide, where the nitrogen is attached to the ring, is a group 2. So that should be our priority group. It's an ortho para director that both of the orthos are blocked, only the para is open. So that is where our acyl group should add. giving that's a little this product here. So doing things in excess, you're just going to do them as many times as you can. So for this one, we have group 1. It can add here, here, and here. When you're doing an excess, you're just going to add all 3 positions. So I forgot the method on this one. For this last one here, we're doing the same thing. So we have an ortho para director. We're adding nitro groups. And you can make this product here. For whatever reason, your book says you can't actually add 3 nitro groups to a molecule. That's definitely untrue. This is TNT here. It's trinitrotoluene. They've been making it since the 1800s. So I don't know why your book says that, but you can definitely add more than 1 nitro group to it. All right, so we're going to finish up chapter 18. We're going to talk a little bit about chapter 22 today. We're just going to pull like 1 series of reactions out of it that deal with aromatic rings. But we're going to start off by doing some review. So talking about the nucleophilic aromatic substitution reactions. We kind of left off on them on Wednesday. So if I take this bromobenzene or nitrobromobenzene, where my nitro is in the either the ortho or the para position, I can do a reaction where NaOH is going to attack the ring at where this bromine is. Create a non-aromatic intermediate. To get final product, which is where OH replaces Br. So this reaction is useful because it lets us create an alcohol, but it's also somewhat of a pain because I have to have this group here in order to do the reaction. If I don't have that group, it doesn't work. So today in chapter 20, we're going to talk about a way to avoid this and go through a different pathway, which lets us just add the alcohol straight to it, as well as a few other groups. But before we do that, I'm going to talk about one last reaction from 18, which is the addition-elimination reaction. This involves generating triple bonds on a benzene ring, which is going to be really unstable. So if we take chlorobenzene again, and this time throw in a pretty strong base, so NaNH2 in ammonia, followed by H3O plus to quench it. What can happen is our base can actually pull off the proton. We're going to make what's called a benzyne. It's a triple bond on a benzene ring. This is going to be really reactive. Another NH2 can come in. Attack this, we'll kick the electrons out. This is going to be one way to make aniline, which is an amine on a benzene ring. No, this should be NH3. We're going to lose a proton, and then we're going to pick up that proton in this step. To get I'll put it here. Aniline, which is basically benzylamine. Another word for benzylamine. Okay. So this reaction can get complicated because this step here, where you attacked your triple bond here, there's no reason why you couldn't have attacked it on this side. Didn't really matter for benzene because it's symmetrical. But if I take toluene, it's going to change it a little bit. So throwing in a methyl group makes our reaction a little bit more asymmetric. Because when I put my base in solution, now when I get this triple bond, I've got two distinct positions that my amine could come in and attack. It could either come and attack here or here. They both will lead to a product. So I can either get my amine to be para or meta. Which is why these reactions are a little bit of a pain, because you can end up with two different products. You can actually end up with three different products if you put it in the meta position. But this is actually going to give you one major product from it. Okay, so if we have it in the meta position, we could eliminate this H here, but we could also have the other resonance structure. Where we have the H on the other side of it. So these both can lead to two different triple bonds. Oh, what are those? Which are going to be these two. They both have a triple bond in the meta position. So they both have it attached here. But now we have both the para and the ortho position are touching the triple bond at some point, which means all four of these can lead to a product. These two are the same, so they are going to lead to the same product. And we could get an amine at all three positions here. It's pretty random how it adds. So most likely we're going to have 25% add para, 25% add meta to this triple bond here. We'll have 25% add meta to this triple bond, and then another 25% add ortho to this triple bond. So because of that, the meta is going to get attacked twice. And we're going to have more of it. So that'll end up being our actual major product from this reaction, just because it's on both sides of that triple, or both triple bonds that it can be created. All right, so that is chapter 18. I'm going to talk a little bit about chapter 20 and really just covering or maybe 3 reactions from it. We're not going to go through any mechanisms from chapter 20. I'm just going to give you a pathway in order to get certain products. And it's going to be all based around diazonium salt formation, which you guys may have covered in the lab by now. Okay, so if I take benzene and I throw in nitric acid and H2SO4, I can add a nitro group. That's the reaction we've talked about. If I throw in H plus and platinum, there's 2 ways to do this reaction. You can either do H plus and platinum or iron, HCl, and heat. Both of them will reduce a nitro to an amine. So you're reducing the double bonds to oxygen, kind of what you would expect an H2 to do. So it lets you go from NO2 to an NH2. So those are all reactions from chapter 18. The chapter 22 reaction is going to be the next one, the next 2 technically. So if we throw in Na, NO2, and HCl, we are going to make N2. You might also see it drawn as an N2 here. This is a really good leaving group. So we're going to do a bunch of nucleophilic aromatic substitutions that are just going to happen in one step. We're just going to easily replace this diazonium with a couple of different things. All right, I'm going to redraw this on another page. All right, so taking our diazonium that we just made, we can do a bunch of different reactions. First one is going to be something that we already know how to do. It's a little less interesting. So if we add in copper and a halide, so CuX, where X is either Cl or Br. Let's do copper chloride for this one. We can brominate or chlorinate, sorry. So not that exciting of a reaction. Going through that whole pathway to add a chlorine is not very useful. So some more interesting reactions. If we throw in B or HBF4, this is going to let us fluorinate. And this is the only way that we know how to fluorinate. So I'm going to put a star next to it. Which means if you ever see a fluorine on your molecule, you're going to have to go through this pathway. All right. Throwing in H2O and heat is going to let us make an alcohol. This is really useful because unlike this NAS pathway that we went through earlier, we had to have this amine here, or this nitro group here for this reaction. We can avoid that entirely and add an alcohol to something that is just a bare benzene ring. We can add copper nitrate, so CuCN, in order to get a nitro group on our molecule. And the last one I'm going to talk about is H3PO4, which will let us remove this entire group and just give you an H on there. So gives you back benzene. Okay, that's all the reactions I want to cover from 22. It's just a way to make a couple of different interesting molecules. Let's start with this one too. So let's take a look at some synthesis problems that use this and talk about a strategy. Let's do the fluorination one now because we're just talked about it. So if I have benzene and I want to make this metachlorofluorobenzene, so Cl, F, they're meta to each other. Taking a look at this, I know I'm gonna have to chlorinate. I know I'm gonna have to fluorinate, which means I'm gonna have to go through that diazonium pathway. It's the only way we know how to make fluorine. I know they need to be meta to each other, which means that I'm gonna have a meta director at some point in order to do this reaction. So if I just try to chlorinate, I'm gonna run into an issue. Oh, you're dead, okay. I'll go in the trash. So let's add in Cl2, AlCl3. Now I have a problem. This is a group 4. It's an ortho para director. If I try to do my pathway to make this fluorine here, the first step is throwing in HNO3, H2SO4. I'm going to get an NO2 in the ortho position and an NO2 in the para position. But what I wanted was it in the meta position, which means these are both dead ends. So I can't do the chlorination first. If I try and do the diazonium formation first, so throw in HNO3, H2SO4. Now I do have a meta director. The next step of this was to throw in H2 and platinum. That gives me an amine. Now I have an ortho para director again, which means that this is the point here where I'm probably going to want to do my chlorination. Because I don't know if I'm ever going to get back to a meta director. So I'm better off just doing it whenever I can. So I have a meta director here. If I throw in my Cl2, AlCl3, I can chlorinate. And then from here, I'm just doing the diazonium pathway, which you guys will get used to because you're probably gonna have to do it a bunch of times. And it's always the same reactions. So H2, Na, NO2, HCl, so that makes my diazonium. I want a fluorine on there, so throwing an HBF4. And anytime you need a diazonium, you're going to do these 4 steps. Or I guess 3 steps, and then some sort of reaction with the diazonium. So when you're studying, those are 3 to kind of put together in your head. That doesn't look right. Okay, I'm going to talk about one more synthetic strategy that you guys are going to see a lot. And it is going to be based around acylations. And then I'm going to give you guys some synthesis problems to work through. So something we talked about briefly, this marker step 2, is if you take a benzene ring and you throw in an acyl chloride like this, we can make this ketone. And if we throw in zinc, mercury, this is Hg. Hg is the symbol for mercury. Oh, that really smirked together. Okay. And HCl. This will give us the alkyl version of this. So why do I care about this? The reason I care about this is that this here is a meta director. This is a group 5. This is an ortho para director. Which means if we're doing a reaction, let's say we have 2 different synthesis we got to do. No, wait, no, I don't want that on there. So we have these 2 here. One of them I chlorinated meta. One of them I chlorinated para. So the way that I would do this, because this is going to rearrange if I try to just add it as a regular alkyl group, is going through an acyl intermediate. So if I take this acyl chloride, here, I can, at this point, chlorinate. I've got a meta director. If I want to get this chlorine product here, I can throw in Cl2, AlCl3. 2-chlorinate meta, followed by reducing this with zinc, mercury, HCl to get this product here. Versus if I try to do this on the bottom, I'm going to have to switch these two steps here. So forming the acyl intermediate. Oh, I ran out of space at the bottom. Yeah, redraw it. From here, if I try to chlorinate, it's going to add meta. I want it to add para, so I need to throw in my mercury first. So zinc, mercury, HCl. Well, let me just get the alkyl. And then from here, I've got an ortho para director. I can throw in Cl2 to get my product. So this is something you guys are going to see a lot. You're probably going to have to add some sort of alkyl group and then decide whether or not you want to reduce it or do your next reaction. So I'm going to do, do I have an example of that? Or no, I'm going to give you guys some problems to work through. And we will go through the first one before the end of class and then the other two at the start of class the next day. So I'm going to put these three up here. And I'll give you guys about 8 minutes to go through them, and then we'll go through them together. Go through the first one. All right, a couple of different ways to do this. First one, I'm going to go through one way where I do the methylation first. Technically another way where you do all the nitrosylations first and then do a methylation. But I like this way better. So I'm going to do methyl chloride, AlCl3 to make toluene. From here, I'm going to have to add fluorines. So I'm going to have to go through my diazonium pathway. So let's try nitrosylate. So if I add in HNO3, H2SO4 in excess, this is an ortho-para director. So it's going to add NO2 to all of those positions, throwing in H plus and H2O, sorry, H2 and platinum. That's will get me to my amines. I can throw in NaNO2 with HCl to make diazoniums. And then, I guess they should all be in excess. Although technically, because it's not selective, you could just write normal. But HBF4, in order to replace all these diazoniums with fluorines, will get us to our final product. All right, I'm going to stop here for the day. On Monday, we will do these other two synthesis problems, do some NMRs, and possibly start on chapter 19. One.